very good morning. Welcome you all to this NPTEL course on electrical distribution system analysis, and today we will be talking about optimization techniques. First of all, why do we need optimization techniques for electrical distribution systems? Let us understand, in a distribution system in the past used to be full of distribution transformers, capacitor banks, distribution lines as well as loads, and very few generating points within a distribution systems. However, today the distribution system has completely evolved with multiple injection point, that means multiple generation points as well as multiple load points. So, the target, especially in case of transmission system, as you are all aware, optimization means minimum cost. That is, how do we cater the customers through minimum cost of generation, so that the electric bill will be very minimum. But in case of distribution system, the objective is not necessarily to be the cost minimization approach. However, that could be loss minimization. For an example, if you alter the voltage at different nodes, probably that will decide your distribution system losses. So, the volt at a particular bus will be my control variable, and the losses could be minimized through a optimization technique. So, let us get into in detail, because optimization technique is very fast and we try to cover almost everything that is available in the current scenario being covered in this content. However, I request all of you to get into the study materials very much in detail, line by line, page by page, to make sure that you capture the concept of optimization technique nicely. But today I will try my best to at least give you an idea how this is being used in distribution system and the gist of optimization technique for the overall benefit of the student community. Now, the background is that distribution system traditionally passive, as I told you, and reliant on pre-designed rule-based methods and controlled by local measurements, mostly using devices like capacitor banks and voltage regulators. Sufficient due to predictable loads and absence of local generation resources. But today, it is not the same story. Today, high penetration of DRs, EVs, bidirectional power flow and smart metering. Variability of renewable generation and demand generation stochastically causing system level problems. Voltage limit violations, increased voltage variability, three-phase voltage unbalance, thermal limit violations, they are becoming new features to the new distribution system today. The control requirements are mainly need for coordinated operation of control devices, including new resources, avoid unnecessarily mechanical operation of devices like tap changes and capacitor banks. So, now it is expected that the grid edge resources provide new grid services such as capacity, flexibility, ramping, voltage support and development of advanced application to actively manage grid edge resources. Now, considering the optimization, the first one is optimal power flow methods emerged as a mechanism to optimize distribution system operation for various grid service requirements, and distribution level OPF, popularly known as D-OPF, present distinct challenges due to unbalanced loading, radial topology and high R/X ratio. Necessitates integration of battery storage, smart inverters, capacitor banks, voltage regulators and secondary voltage controllers, which results in mixed integer decision variables and intertemporal constraints. Now, stochastic optimization requires inclusion of multiple sources of uncertainty from model and measurement data. Computationally, interactable stochastic optimization formulation is quite important, and majorly the grid service support, that is DRs, provide grid services at distribution or bulk grid level. Service includes capacity, flexibility, ramping, as we discussed earlier. Many services are being validated through field demonstrations. But we need to formulate the OPF problem. So, there will be objective function, there will be equality constraint and there will be inequality constraint. And the objective function could be generation cost minimization, could be loss minimization, could be voltage deviation minimization. There could be n number of issues that can be formulated. Now, looking into different optimization techniques, we will start with hierarchical optimization, coordination between distribution level and wholesale market. Hierarchical or distributed optimization approaches manage computational complexity and data privacy. Now, in case of nonlinear distributed OPF formulation, they are solved where only continuous decision variables are modeled, bus injection or branch flow power flow models are used, and nonlinear power flow equations cause nonlinearity. In case of linear or convex optimization, approximation or relaxation of power flow equations produce simpler formulations, and the real world problems often required mixed integer nonlinear optimizations. Now, let us look into this table, which is quite interesting, which talks about different distributed OPFs like nonlinear model, linear approximation, convex relaxation and mixed integer models. And OPF do use power flow inbuilt within it, because you cannot carry out a optimal power flow without calling power flow again and again. So, power flow is one short solution, and you have to have multiple power flow solution to obtain a optimal solutions or optimal power flow solution. Now, power flow we can use, for example, nonlinear models, we can use bus injection model or branch flow models. We will look into those formulations very much detailed in due course of time. Linear approximate model, which is linear distinct flow, other linearized models. In case of convex relaxation model, we move to semi-definite relaxation, second order cone relaxation. In case of mixed integer model, nonlinear power flow models, linear approximate model and convex relaxation models. And the optimization models are sometimes actually NLP or LP or SDP or SOCP. This SDP and SOCP is based on actually the bus injection or actually line models. So, bus or line models actually are renamed as SDP and SOCP. We will discuss in detail actually in due course of time. And then mixed integer nonlinear programming and mixed integer linear programming are also part of MILP model. And the decision variables are continuous, and some of the cases it is continuous and discrete. Why this discrete is available? Discrete means for example, switching voltage regulators or switching capacitor banks, they are part of your discrete variables. Coming back to controllable devices, I mean there are so many controllable devices which is part of your distribution system, such as voltage regulator, capacitor banks, feeder switches, PV with smart inverters, BSS, EVs, BMS and DGs, and then you have STATCOMs, UPFC, SBCs and many devices. They are being part of your distribution system, which can control some of the major parameters like I, V, P, Q, theta, delta based on the requirements. So, you can see what are those control parameters. For an example, if I talk about a voltage regulator, tap setting could be my control variable and which is discrete. Now, moving back to capacitor bank, on off status become my control parameters and they are discrete. Now, moving quickly to EVs, where active power, charging and discharging become control variable and they could be continuous and discrete. That means the controllable devices of distribution system will have certain control parameters and those could be either discrete or continuous in nature. Now, let us move to notations for network modeling. A radial distribution system is represented as a directed graph, which is G equal to N and E, where N denotes the set of buses and E denotes the set of edges. Now, again we can define what is an edge. Okay. I strongly recommend most of you to get into the basics of this fundamental of network modeling in detail. So, edge is defined joins two adjacent nodes of I and J, where I is the parent node for the node J. Similarly, in case of three phase, we define it is ABC for a node I. In the distribution system is denoted by phi I, which is of ABC. So, when we represent A means phase A, B means phase B and C means phase C. So, now let us see how the voltage and the complex power are being defined. The moment you say VI means represent the complex voltage, SLI represent the complex power demand, and SDGI represent the complex power generation. So, generation, demand and voltages are being defined in this order or in this pattern. Now, let us get into the vector notations for your 3 phases. So, I think VI, which is matrix of VI, and SLI and SDGI can be defined in this fashion. Now, for each line, let psi phase current be defined as Iij psi and define Iij, which is again a matrix of actually Iij psi for all 3 pages. Now, dot H represent the conjugate transpose and J, which is under root of -1. Let Zij be the phase impedance matrix for the 2 terminal devices such as distribution lines or transformers. Now, in case of distribution optimal power flow D-OPF notation, we can say let Vi, which is diagonal of Vi and VIH, represent the complex conjugate, and dot T denotes the matrix transpose, and J, which has already been defined as under root of -1. Now, try to understand voltage regulator and what is voltage regulator. So, voltage regulator characteristic, as we all know from our undergraduates, that it is basically 32-step voltage regulator. And if you haven't learned, probably this is for the first time for some of the learners. So, there are 32 steps through which the voltage being regulated, and the range of voltage to be regulated is close to plus or minus 10%. Am I right? So, it is something like, let us say if the voltage is going to be 1 per unit, all right. So, you can do it from actually 0.9 to 1.1, it can vary between this range, and there are 32 steps. Okay. So, that means basically you have to 0.2 divided by 32 will give me the range through which it can vary in per unit basis. So, that value will be approximately 0.00625 per unit. So, in each step I can change 0.00625 per unit, and in 32 steps I can vary between 0.9 to 1.1, that is plus or minus 10%. An additional note IDES is introduced to model the current equations too. Now, the control of regulators is defined using binary variables. Let U tap, which is 0 or 1, for be a binary variable defined for each regulator step position, that is I is varying from 1 to up to 32 steps. So, that means also define a vector which is 0.9 to 1.1, and as I told you that each step will be 0.00625. So, the first step is 0.9, the second step let us say 0.90625 plus 0.00625, and if you do it for 32 times, finally you will land with 1.1. Now, voltage and current equations, which is Vj, Vi dash, AVi as well as II dash, which is nothing but A times I dash J, where A psi is defined as step number 1 to 32 B times Ui tap, whereas the summation of Ui tap I equal to 1 to 32 is equal to 1. Now, square of voltage and current equations, where we can define that A psi square, which is A psi, capital A psi, and Bi square become Bi, and reformulated as defined by Vj, which is Vj psi, which is A psi times Vi psi, and similarly II dash psi psi equal to A psi II dash J psi. Now, just for basic understanding, that when you formulate mathematically for your optimal power flow solutions, we need to accommodate the philosophy of voltage regulator in the form of equations, and hence you have been advised how those 32 steps 0.00625 increment in 32 steps can be achieved through a mathematical formulation. Now, similarly, if you think about a capacitor bank, so the reactive power generated by the capacitor bank, which is Q cap, is a function of binary control variables, which is either 0 1, because sometimes the capacitor is on and sometimes it is off, indicates the status of on/off of a capacitor bank. So, how do I model or incorporate in my original formulation? So, the reactive power equation, which is given by Q cap, that is capacitor reactive power, which is U cap Q cap multiplied times VI. The capacitor bank model is assumed to be voltage dependent and provides reactive power as a function of VI square when connected, that is U cap I equal to 1. For a three-phase capacitor bank, a common control variable U cap I is defined for each phase, that is for phase A, B and C. Now, let us focus on distributed generation with smart inverters. Means, let us say we have a PV plant connected with smart inverters. That means the reactive power injection, the received from the grid or given to the grid can be controlled. That means a per phase model for reactive power support from smart inverter connected to distributed generation is developed, and the distributed generations are modeled as negative loads with a known active power generation equal to the forecasted value. Now, the reactive power support from the DG depends upon the rating of the smart inverter. Let the rated per phase apparent power capacity for smart inverter connected to the ith DG be considered as SDGI rated psi, and the forecasted active generation be PDGI psi. So, the available reactive power, that is QDGI psi, from the smart inverter is given by, so this must be, so the QDGI, the reactive power available to me from the smart generator, must be less than this and must be greater than this. So, this is indirectly a range between which the reactive power of the smart inverter can be extracted. So, this is kind of a inequality constraint during my OPF formulation. Now, we can also think of a battery storage device which is part of your distribution system, and in this case of BES, where actually you need to have actually SOC. So, BES considers 4 quadrant operation capability, both active and reactive power, positive, negative, charging and discharging characteristics. So, you will have charging, discharging, positive, negative, and for both active and reactive power. Okay. So, when you talk about state of charge SOC update equations, so you can use the SOC equation, which is quite standard, and these are the battery constraints to be considered, and the apparent power, which is charging plus discharging square plus QI BISS, must be less than about its maximum capacity which is available to me. So, this is how the apparent equation must be satisfied. Now, let us get into bit of power flow equations. So, bus injection model, which is power injection form. So, in case of bus injection model, first of all, if you write the power injection form, which is very standard, almost similar to your transmission systems, which is S, which is equal to V YV conjugate, can be given in this equation, where V is nothing but my V1 to nth node, and Y, the admittance matrix, is nothing but of this shape. Now, in case of polar coordinates, the same equation can be defined for QM as well as for PM. And for the current injection form I, we can write it down. The previous case, as you could see, which is power injection form, so we have gone for S. Now, we are talking about current injection form, which is I equal to YV, can be given a summation of YJI Vj, where I is given by a matrix form, bus number 1 to nth one. So, power injection equations for non-zero injection buses is given by S, diagonal S, which is diagonal V times diagonal I. So, the number of nonlinear equations in the current injection form depends on the number of non-zero injection buses, while in the power injection form, this depends on the total number of buses on the network. So, this need to be highlighted, that the number of nonlinear equation in the current injection form depends on the number of non-zero injection buses, while in case of power injection form, this depends on the total number of buses on the network. And now, let us focus on branch flow model. So, these are all different methods. Everyone most probably give you the same solution and may be suitable for small size systems, may be suitable for large size systems. Someone may be complicated to formulate, someone may be easy to formulate, but the concept of each and every mathematical model is, at the end of the day, the power flow and the optimal power flow equation formulation. Now, when we talk about branch flow model, what is it? So, nonlinear BFM, so-called branch flow model. So, the mathematical formulation for a power flow model based on branch flow equations for a radial distribution system. So, for a radial system, it is simple, all right. Okay. So, this is my radial network where the Vj, which is nothing but Vi injected voltage minus ith bus voltage minus the drop in the line. Okay. So, similarly you can formulate these equations where Sij, which is equal to Vi Iij times H. So, the model can be modified to incorporate distributed energy resources. Okay. So, that case this term SdG may be subtracted. So, that will give you a modified model, because in the past actually we never used to consider that there could be some distributed generation present in the distribution system, but for last 1 decade, which are very common. So, all distribution power flow equations need to be reorganized, considering that there could be a injection through PV, wind or some small diesel generators. So, moving to the next one is branch flow model. So, in case of branch flow model, there are different parts, especially the linearized 3-phase AC power flow. This linear power flow approximation assumes that the branch power losses are relatively smaller than the branch power losses. So, that can be ignored, and probably the power equations for both real and reactive can be of this form. So, the linear distribution flow model is accurate in representing bus voltage under normal loading conditions. It incorporates the impact of power flows due to load on voltage drop calculations, and the obtained feeder voltage are a good approximation of the actual feeder voltages. Now, there are different algorithms available to solve distribution power flow models, and majorly and popularly they are forward backward sweep method, Z-bus approach, that is fixed point iterations, and then you have Newton-Raphson power injection form and Newton-Raphson current injection form. Just to give an idea about forward backward sweep method, let us understand in any substation, okay, considered to be, this is my substation, am I right, and there is a radial feeder, all right. Now, if the load P plus J cube at this bus is known to me, similarly at this bus and similarly at this bus, because the loads are considered to be known to me, and line parameters are also known to me, and with an assumed voltage at this bus, okay, let us say it is Pi, Qi and Vi. I can easily calculate the current, injected current, and by knowing this current, knowing the line impedance, I can calculate the Vj, I can calculate Vm, I can calculate the Vn. But the substation injected voltage will be certainly 1 per unit for an example. So, there will be a mismatch between my V standard to my calculated Vn. So, I moved one direction from load point to the source point, and based on the new voltage calculated and the old currents that are known to me, I can again move from this point to this voltage, to this voltage, to this voltage. Again I will reverse back. So, there will be a forward backward sweep happens till the time there is no variation in my voltages in couple of iterations. Once the voltages are stabilized, so then the line currents of each feeder become frozen. So, this method is known as forward backward sweep. Similarly, we have different methods for Z-bus approach, Newton-Raphson methods and Newton-Raphson method with current injection too. Now, we talk about importance of modeling software. Naturally, when you go for implementing your optimal power flow, especially D-OPF, that is distribution OPF, then we need to have certain algorithms, and they could be either available ready-made as a tool in your MATLAB, or there could be open sources, or probably you can write your own coding. Okay? So, these are the 3 opportunities available to you. So, necessary for detailed feeder and equipment modeling, but software modeling is mandatory. That is what I wanted to highlight. So, supports advanced distribution system analysis and can be developed using programming languages like C++, Python, or you can use some of the tools within the MATLAB. So, the commercial software for distribution system modeling, which is also available, which is for the utilities like CI Midist, Synergy, and WindMIL. So, these are all commercial softwares available for utility applications and proprietary and not easily accessible to the research community, because they are very expensive as well as used for the industry level applications. Now, there are very interesting economical open source distribution system simulators that are available to us, and they are publicly available. For example, you can use OpenDSS, you can use GridLabD, or you can use PandaPower. Okay, and these are the links for your benefit given to you. You can download those softwares and use or solve your load flow as well as optimal power flow for distribution systems. Now, after that, let us get into the OPF formulation. Okay, so we do have different control variables. So, with different control settings, you will have different power flow solutions, and we keep on repeating these cycles, and then we converge to a control variable which leads to optimization of a specific objective defined by the user. Could be loss, could be voltage variation, could be of any form. Now, key applications includes loss minimization, volt var optimization, and managing distributed energy resources, that is DERs. So, it is quite important that we make sure that such objectives are being achieved. That means minimization of losses, volt var optimization means optimizing volt var requirements, and so on and so forth. Now, increased distributed energy resources, proactive loads, and demand response programs necessitates advanced optimization methods for large scale systems. So, the new requirement are driving the rapid adoption of ADMS and related application for effective grid management. Distribution level OPF faces challenges like three-phase unbalanced loading and radial topology. Recent advancements have improved three-phase unbalanced distributed OPF formulations. Now, let us see how the basic distributed OPF formulation look like. Let me explain bit in detail. So, the D-OPF problem formulation formulated as constraint optimization problem with an objective function and system level operational constraints. So, first of all, you will have the objective function, which is minimization or maximization of a specific objective with equality constraint as Gxu equal to 0 and inequality constraint of Hxu less than or equal to 0. So, this is a very basic standard format for your optimal power flow, where X defines state variables representing power flow quantities, U defines decision variables either continuous or integer, Fxu is the problem objective, and Gxu is the equality constraints for power flow equations, and Hxu is the operating constraints for state and decision variables. Now, distribution optimal power flow formulations, again we can define as minimization of total power loss, or we can have maximization of PV hosting capacity, and they can be defined in any form as a minimization or maximization problem. We can also define as minimize the voltage deviation from set points. So, that means you do not want to experience a major voltage deviation from the reference point. And similarly, we can also have an objective that minimize net load demand. So, as per the requirement of the utility or the user, the problem of D-OPF can be defined with different objective functions, as we discussed that power loss minimization, PV hosting capacity maximization. We can talk about actually voltage deviation from set point can be minimized, as well as we can minimize the net load demand. And we do have different constraints, that is power flow constraints, so which are non-linear equality constraints. We have voltage limits. The V at any given point of time must be between V minimum to V maximum, Either it could be 0.95 to 1.05 or 0.99 to 1.01 or zero point 0.9 to 1.1 depending upon the utilities requirement. We can also have different thermal limits as well as DG operating limits. So, the DG power output must be less than or equal to its maximum rating capacity. And then we have different decision variables which are important for all of us to understand. So, voltage regulator, which is a decision variable of 32 steps, capacitor bank, which is on or off, that is 0 and 1, and similarly distributed generators, which has to cater active and reactive power requirements, and they could be also controlled because I can decide what is my PDG and QDG to achieve certain goal in my objective functions. And there are different algorithms. I am not really getting into too much details here. So, the philosophy is very clear. In case of optimal power flow, we will be having certain objective functions. Then we have certain actually inequality constraints and equality constraints. And in case of distribution systems, the objective function could be loss minimization, could be voltage fluctuation optimization, could be minimizing the load requirement, could be an objective function. So, you can have any objective functions with different control variables that could be your capacitor banks or voltage regulators, or maybe the variation generation output real and reactive of distributed generations. And there are different algorithms available for you such as D-OPF using bus injection power flow model, which is known as popularly NLP BIM. All the study materials will be made available to you, and I expect you to get into very much in detail to understand more about the detailing of optimization techniques. Now, this is the formulation, and you can have different constraints such as power flow constraints and operating constraints, and you can also have actually power flow constraints. So, this is basically your bus injection power flow model, NLP BIM, and the second one, again you can have different operating constraints for your voltages, you can have operating constraints for your currents, and the same bus injection power flow model where actually you can also consider the reactive power requirement QDG become less than or greater than a particular range, and you can also consider the constraints for PV hosting maximization capacity assuming active power control. Now, similarly, instead of the previous cases we discussed about bus injection power flow model, we can also consider branch flow power flow model. The formulation is slightly different. Again, the objective function, power flow constraints, operating constraints, as well as PV hosting maximization, as well as voltage deviation capacity. So, popularly, I mean, this is known as SOCP, if I am correct, and then probably we'll look into these models actually in due course of time. Then we have certain approximation of relaxation technique, which is nonlinear relationship in OPF. So, OPF problem is quite non-convex, okay. So, what do you understand by non-convex? For, those who are learning OPF for the first time, you see when you talk about any function, if you plot a characteristic which is nonlinear, okay. But this characteristic, if you say this is a characteristic with multiple optimal points, am I right, is ideally known as non-convex. If the function is simply has single optimization problem, either this or this is probably known as a convex characteristic. Okay, so this is my convex and this is my non-convex. So, in case of non-convex, the challenge is your solution may be trapped into a suboptimal solution, okay? Because now if you start your initial point here, you get into iteration, come and then finally you get settled at this point. So, probably there could be another optimal point, okay? This is the minimization problem, let us say. So, this optimization problem, optimal solution you are not able to capture because your initial point started from this. So, it is quite important for non-convex optimal power flow solutions, the mathematical formulation become challenging and getting the true solution become an issue. So, NLP model for unbalanced distributed OPF can lead to infeasible or suboptimal solutions, especially for large or mid-size feeders. Recent research focuses on scalable algorithms for unbalanced distributed OPF that achieve feasible and optimal solutions. Relaxation based approach, relax nonlinear power flow equations into convex inequalities, results in a convex optimization problem for distributed OPF solving within reasonable time for large scale distribution systems. Now, common methods include BIM based D-OPF, which is popularly known as SDP, and BFM based distributed OPF is popularly known as SOCP. Okay. So, SDP and SOCP are very popular and commonly used by utilities. So, then one more technique, which is conic relaxation or semi definite program, lead to a convex problem formulation by relaxing nonlinear inequalities constraints into convex inequality constraints. So, this is another method which is popularly known as conic relaxation. This is the formulation, objective function, power flow constraints, operating constraints, loss in voltage deviation minimization, and PV hosting maximization formulation. Now, we can also have a linearized three-phase model obtaining using lifted branch flow equations, involve two major approximations, ignoring power losses and approximating nodal voltage phase angles. So, again the formulation will be of this structure: minimization, power flow constraints, operating constraint, thermal constraints for three-phase, loss and voltage deviation minimization, as well as PV hosting maximization. Now, there are a couple of hybrid models are being used, which is known as second order cone programming. So, the hybrid model incorporates elements of both approximation and relaxation. All right. So, the approximation involves ignoring the mutual coupling in three-phase lines, okay, and the results of three-phase branch flow equations written separately for each phase. Now, the resulting nonlinear power flow equations are then relaxed to obtain a second order cone programming model. So, this is how the approximation being carried out and then the relaxation being carried out. So, approximation of impedance matrix and then power flow model, convex relaxation model, and finally, we talk about an objective function, power flow constraints, operating constraints, loss and voltage deviation minimization, PV hosting maximization. Now, there is one more thing known as AC feasibility of the solution obtained from the relaxed distributed OPF model. So, the OPF solutions are AC feasible if they satisfy the equation which is given by Pij square plus Qij square equal to Vi times Iij. If the OPF solution do not satisfy this equality, they are AC infeasible and meaningless. So, similarly, we have actually multi-period distributed OPF formulations with intertemporal constraints, and then we can develop the multi-period distributed OPF, and then we have time series nature of some distributed OPF problems and decoupling multi-period problem too. Now, to conclude, all these formulations, we discussed almost the history of optimal power flow today. I do agree that it is not easy to digest the amount of the magnitude of optimization that we have covered today, but I request once again the amount of study material made available to you. If you go through carefully, probably you will be quite confident. Once you capture the thought process that I have tried my level best to make you understand what is load flow, what is optimal power flow, and why it is important for distribution system, and what are the algorithms and techniques available. Now, bit of MATLAB optimization toolbox that you can use during your assignments, or maybe for your self-learning or for your projects that you work in this field. And you can use the toolbox such as LP, MILP, QP, and NLP problems with functions like Pimicon, okay, and for NLP and int, lin, proc for MILP. So, these are the toolboxes you can use. Optimization toolbox actually provide multiple algorithms for each class of optimization problems. There are a bit of external solvers available: Cplex, Kintro, Gurabi, very popular, HDPT3, SUDUMI, Mojek, again popular, and GLPK. Okay, these are the external optimization tools. External optimization tools can be also used for your application. Now, dedicated MATLAB based software packages, which are MATLAB based software for modeling and solving convex optimization problem. It is CBX, popularly known as CBX, you can call this function. Support mixed integer discipline convex programming, MIDCP, include SDPT3, SIDUMI solver, and support Gurobi, Mojak, and GLPK. Dedicated MATLAB based software packages, that is while MIP, MATLAB toolbox for modeling linear programming, MILP, SOCP, SDP, QP, MIQP, NLP. Today, we are popularly using Python. Multiple Python based and open source optimization modeling platform are also available. One of the popularly available Python based optimization tool is known as CVX OPT. This is a free software package for convex optimization, which is also capable of interfacing with GLPK, DP5 as well as Mojak. And Python based optimization tools such as PyMo, PULP, SCIPY, and Gurobi P. Finally, we do have actually one more application popularly known as Julia and JUMP. Julia is a dynamic language used extensively for scientific and numerical computing, and JUMP is a modeling language in Julia for optimization problems. So, JUMP supports multiple open source and commercial solvers for linear, mixed integer, second order, conic, semi-definite, and nonlinear programming application. So, with this we come to an end of today's lecture. Thank you very much for your patient listening. Bit of conclusion remarks that you can let us summarize what you have learned as of now very quickly. So, the challenges and distribution OPF algorithms. So, a practically viable distributed OPF algorithm must obtain an optimal and feasible solution faster than the changes in distribution system operating condition. That means you have to get this solution before the load dynamics changes, all right, and that is why the optimal power flow become important. The load scenarios keep on changing, let's say every minute, every second, every 5 minutes. So, you have to have a quicker and optimal load flow algorithm to conclude or obtain optimal power flow solution before the load dynamics changes. And we have also made many conclusions out of our discussions. So, please go through all the conclusions. Thank you once again for your patient listening. Thank you.